So to find this joint density function, once again, if you look at the autocorrelation function of Rxx and Ryy, that's sigma squared rho tau, and Rxy, the cross correlation function is in terms of gamma tau. So I'm going to quickly sketch the results. So I start with this vector. We have 4 random variables here, x1, y1, x2, y2. So we want the autocorrelation function of expected value of xx transpose. Notice that all these are, so this corresponds to time instant t1. This corresponds to a later time t plus tau or t2. And everything is real random variables. And if you, so you can use these functions to compute the, so autocorrelation function will turn out to be, I'll write it down here. So this will turn out to be the, remember this, this rho function is going to be rho at tau. Tau is the difference between t1 and t2. This is t1, this is t2. T2 is t plus tau. So the determinant, if you do this quickly, determinant will turn out to be sigma 8 multiplied by 1 minus rho squared minus r squared. And I'm going to write this as sigma 8 multiplied by 1 minus standard notation k squared tau, where k squared tau is rho squared tau plus gamma squared tau. So notice that this has to be less than 1 because this is greater than 0. If these random variables are not completely dependent, then the determinant is going to be positive, and consequently that's less than 1. So we need R inverse. The inverse is going to be 1 over sigma squared 1 minus k squared. When I say k squared, it's actually I mean k squared tau. Then it's going to be 1, 0. You can do it. I did it. Again, this is actually a standard result. So nothing new here, except all the details are generally hard to find. So this will turn out to be R inverse. And now we are, once with the R inverse, we are ready to write down the joint density function of x1, y1, x2, y2, which will turn out to be 1 over 2 pi squared r to the power half. This is a standard expression, x squared r inverse x divided by 2. So this is the reason I wanted R inverse. So we take this R inverse, plug it in here. The determinant is here, we plug this in here. So I'm going to write down the result. So this will turn out to be all right, there is nothing to it except that you just have to do it. So you take this x vector, multiply it from the left, multiply it from the right, simplify, you will get this much term. So now I'm going to make a transformation to the r theta domain. So I'm going to define x1 to be r1 cos theta 1, x2 to be y1, I guess. Y1 to be, then y1 will be r1 sine theta 1. And similarly, x2 is r2 cos theta 2, y2 is r2 sine theta 2. As you know, the Jacobian, if you do this, will turn out to be simply r1 r2. So I'm not going to r1 r2. So the joint density function of the same density function, but now expressed in terms of r1 r2 theta 1 theta 2 would be 1 over this Jacobian multiplied by the density function. You start substituting these values for r1 and x1. Okay. So if you do that, you can clearly follow it. So you have an r1 r2 because of the Jacobian. Then you have a 2 pi squared sigma 4 1 minus k squared. Notice that this is r1 squared plus r2 squared. So e to the power minus 1 over. So the numerator is going to be r1 squared plus r2 squared minus 2 r1 r2 rho cos theta 1 minus theta 2 by substituting here plus r sine theta 1 minus theta 2. This you can, and the whole thing divided by 2 sigma squared multiplied by 1 minus k squared. Of course, k squared is a function of tau. So I'm going to copy this to that board, except I'm going to make one more simplification because I can multiply and divide by square root of rho squared by gamma r squared and rewrite this as so we get in this fashion r theta r1 theta r2 theta 1 theta 2 to be r1 r2 All right, so because I have divided there by square root of rho squared plus sigma squared, but that's k. Remember, k of tau is square root of rho squared plus gamma squared. And theta naught is, of course, a tan inverse of r tau over k tau, over rho tau. So from here, the next job is to find the joint density function of R1 and R2. That's easy because you just have to integrate out over theta 1 and theta 2. So we can pull out the terms. Remember, theta 1 and theta 2 is only involves on this term. So you can clearly see that this can be written as R1, R2, 2 pi squared, sigma 4, 1 minus k squared, e to the power R1 squared plus R2 squared over 2 sigma squared, 1 minus k squared. So we can write this as, I'm going to take this 1 over 2 pi and write this here. So 1 over 2 pi, two integrals, right? So 0 to 2 pi d theta 2 and 1 over 2 pi integral from 0 to pi, the remaining term. So the remaining term is going to be from here. So minus minus plus 2 cancel. So e raised to r1 r2 k over sigma squared 1 minus k squared cosine theta 1 minus theta 2 minus phi naught d theta 1. But as you can see, this is going to be, this is simply the Bessel function of 0th order evaluated at this point, this whole thing. So this is going to be because this is when theta 1 is the variable, theta 2 and phi naught are constant. So we can simply redo this by changing this variable still over one complete cycle. So this will be I naught of r1 r2 k over sigma squared multiplied by 1 minus k squared. And if I substitute the remaining term, so this is going to be simply r1 r2 sigma 4 multiplied by 1 minus k squared e to the power minus r1 squared plus r2 squared over 1 minus 2 sigma squared 1 minus k squared multiplied by I naught of r1 r2 k of tau over sigma squared 1 minus k squared is the density function for r1, of course positive, r2 positive. This is the joint density function for r1 and r2. As we know, r1 and r2 are both separately, they are Rayleigh. So this is actually the correlated Rayleigh, two correlated Rayleigh random variables. So the question is, how much is the correlation between r1 and r2? That's where we are going to go.